Hi, this is Team D2V from Inha University in Korea. We worked with Professor Hale to create a new social value by integrating a self-driving car and an autonomous drone. We tried to build a system that can be applied to various fields. People are programmed to perceive, think, and action. Suppose a person is driving a car. Through various senses like eyes and ears, the driver collects the information around the car. The brain rapidly compiles the information and plans the optimal action. Soon after, the driver controls the car with their action mediums such as hands and feet. Our system's mechanism is similar to that of the people's. Various senses perceive the information from the surroundings. An onboard computer decides what to do next, and the machine performs the command from it. Based on this principle, a car and a drone operate autonomously. And this is the demo video of a project. The main point of a project is the collaboration between the autonomous car and the drone. Our platform has two main collaborative functions. The first is autonomous driving. A self-driving vehicle carries a drone to its destination. When the car arrives at that location, the drone takes off to search the target object. The second main function is the collaborative driving of the car and the drone. Collaborative driving provides information on the adjacent environment, including the objects that cannot be observed from the car. Also, the drone can detect the target object and send its position to the ground station. The ground station will send the information to the car. And as the car moves to the position, the ground station monitors their movements. Here, the drone's tracking and landing are manually performed to demonstrate the concept. We are still developing these functions, but all others are entirely autonomous. So why does this system matter? A drone and a car each bear limitations. However, we eliminated these problems by building a complementary system between them. When used alone, drones suffer from low battery and limited payload. Often, increasing the battery and the drone size is suggested as a solution. However, it is too costly and inefficient. What about charging the drone wirelessly? It is quite groundbreaking, but there are many tests to reach that level. As we struggled to solve the limitations of the drone, one question came to our mind. What about a car? A car that can carry a larger battery with a sufficient payload. A car that can support the drone for a longer mission. In order to progress, we had to understand the limitations of a car. Cars require a pay floor to move, and the two-dimensional limitation increases the risk of accidents. In this point, we want to highlight the complementary relationship between a drone and a car. A drone can fly to places that a car cannot reach. A drone can collect a bird's-eye view of the surrounding. It can also provide a universal understanding of the current environment. So, creating an interdependent system between a car and a drone is a novel solution to the limitations of them. Then, how would this system create a social value? First, it prevents delay in emergency services. Emergencies in remote areas are not handled timely. The pandemic made the relief tasks even harder to be done face-to-face. Using a platform, we can ensure the speed and safety of these relief tests. Also, our system will enable the coverage of a wider area because the drone will be charged upon the car. Next, it is providing an access to remote places. Imagine places like mountainside and uninhabited areas. It's hard to deploy personnel for emergency tests, such as search, rescue, and delivering supplies. Our system will facilitate these activities in remote areas. Lastly, its cost-effectiveness will contribute to the development of AI. A reliable dataset in a huge size is essential for the research in AI. The sensors mounted on our platform provide a wide range of ground truth data. Our system will lower the cost of collecting extensive, reliable data over a wide area. With the integration of the two unmanned mobilities, these possibilities will turn into all realities. The car and the drone directly identify the surroundings with the sensors. Based on the sensor data, we developed control algorithms that cope with different driving and flight situations. These algorithms run on the computer of the car and the Jetson Nano of the drone. Lastly, we build a collaborative algorithms between the car and the drone using Robot Operating System ROS. We also made a tool for monitoring all our system using Qt and RViz. We spent about $500 and $10,000 on the drone and the vehicle, respectively. For the vehicle, we used an existing platform with a controller computer. For the drone, we assembled it by ourselves. In total, it took about 8 months to develop all the system. Of course, this is not a small amount of cost and time. However, we plan to utilize the existing platform to decrease these costs, focusing on the contribution to human safety and convenience. For this year, our development plan is as follows. First, we will strengthen the reliability of self-driving system for its safety. This will be done by increasing the accuracy of the deep learning-based object detection. And next, the drone will deliver a load of up to 3 kilograms and safely land on the mission place through autonomous flight. We are 19 undergraduate students majoring in various engineering fields, such as mechanical, aerospace, electrical, and information and communication engineering. As a team, we actively communicate with each other and share skills, knowledge, and experience. We keep trying our best to contribute to the solution for real-world problems. This is the end of our presentation. Thank you for listening.